Lesson 4, Uniform Acceleration. 4.1, Acceleration. There are two types of uniform motion. Uniform means the same. Uniform motion refers to motion that is the same. There is uniform velocity, which happens whenever an object is traveling at a constant speed or velocity. Remembering that if an object is traveling at a constant speed, its speed is its velocity. There's also uniform acceleration. Uniform acceleration indicates changing speed, but constant rate of change, or constant acceleration. Acceleration is when an object changes velocity. It's changing velocity. This means it's either speeding up, slowing down, or changing direction. Constant acceleration happens when an object speeds up by a constant amount or changes speed by a constant amount each second. For example, here's a data table that shows how an object's velocity changed each second. At time equaled 0 seconds, the object was traveling 0 meters per second, so it wasn't moving. At 1 second, it was traveling 10 meters per second. At 2 seconds, it was traveling 20 meters per second. At 3 seconds, it was traveling 30 meters per second. So it was speeding up every second. It's constant acceleration because the object increases speed or increases velocity by the same amount, by 10 meters per second each second. We would say that the object accelerates. Its acceleration equals 10 meters per second per second. We could also write this as 10 meters per second squared. Acceleration is a vector. The symbol for acceleration is a with a little arrow above to indicate that it's a vector, and its unit is the meter per second squared. The basic formula for acceleration, and I say basic formula because there's several others that also include acceleration that you're going to learn in a lesson, is a equals delta v, or change in v, divided by delta t, or change in t. Change in v is equal to vf minus vi, where vf is equal to the object's final velocity, the velocity it ends with, and vi is the object's initial velocity. This is the velocity it starts out with. So this formula can also be written, and is perhaps easier if it's written as vf minus vi over t. We'll use this as one of the official formulas for acceleration. Very, very important in acceleration calculations. Since velocity is a vector, plus or minus signs must be included in calculations to indicate direction. If you don't do this, if you don't use your plus and minus signs in your calculations, you will get incorrect answers for acceleration. Here's an example. A car traveling south at 25 meters per second takes 15 seconds to turn around and accelerate to 12 meters per second north. What was the acceleration? As the problems get more complex in physics, we will always start by making a list. This list looks like this. VF equals 12 meters per second north, which is positive 12 meters per second. VI is 25 meters per second south. This is negative 25 meters per second, the negative because of the south. The time it took was 15 seconds. The formula is acceleration equals VF minus VI over t. This is positive 12 minus negative 25 divided by 15, which gives us positive 2.5 meters per second squared. Changing this back into direction, we have 2.5 meters per second squared to the north. Acceleration is a vector. You must give your vector answers positive or negative signs, or directions must be indicated. Direction for acceleration indicates the way you would need to push the object to get the change in motion that you observe. For this reason, acceleration and force are very linked. So acceleration can be thought of as a push. Which way would you have to push it to get the change in motion? For example, let's look at two cases where an object speeds up. First, we have a little car that's traveling with a velocity to the right. To get this car to speed up, we would need to push it in the same direction it's moving. This means to speed it up, the acceleration must also be to the right. Or also consider a little car that's traveling with a velocity to the left. To get this car to speed up, we would need to push it also to the left to get it to move accelerate in the direction it's moving. So the acceleration is also to the left. If acceleration and velocity both point the same way or the same direction, the object speeds up. We're also going to look at two examples of an object that is slowing down. For example, a little car that is traveling to the right, or with a velocity to the right. You would need to push it against its velocity to get it to slow down. This means to slow it down, the acceleration would have to be to the left. Or, if you have a car that's traveling with a velocity to the left, you would need to push it against its speed to get it to slow down. So the acceleration is to the right. If the acceleration and the velocity of an object are in opposite directions, the object is slowing down. It is important that you recognize that acceleration and velocity don't have to point the same way. If the acceleration is the same as the velocity, the object speeds up. If the acceleration is opposite to the velocity, the object is slowing down. Acceleration doesn't have to be slowing down if it's negative. A negative acceleration could mean speeding up, or even a change in the object's direction. An object can speed up in a negative direction. For example, a ball rolls up a ramp at 10 meters per second. The acceleration of the ball is 3.5 meters per second down the ramp. How long does it take to roll back down at 7.5 meters per second? First, we'll start with a picture to visualize the situation. We'll start by drawing a ramp. And the ball is traveling up the ramp at first, at 10 meters per second. As the ball travels up the ramp, because the acceleration is down, it's slowing down. It continues with this until it gets to a point where it stops. It slowed so much that it stopped moving. And then it starts to roll back down again. At this point, it's actually speeding up in the opposite direction. Eventually, the ball reaches the speed where it's at 7.5 meters per second. Throughout all this, slowing down, stopping, and then speeding up again, the acceleration has been the same. It's always been a constant value of negative 3.5 meters per second. The whole time, the acceleration is constant. Now let's solve for the time. We start by making a list. VI is equal to 10 meters per second up the ramp. This is equal to positive 10 meters per second. VF is negative 7.5 meters per second down the ramp. Down is a negative direction, so this is negative 7.5 meters per second. The acceleration is 3.5 meters per second squared down the ramp. Because down is a negative direction, the acceleration is negative 3.5 meters per second squared. The time is our unknown. It equals question mark. The formula is VF minus VI over t gives us acceleration. Time can be rearranged as VF minus VI over acceleration. Plugging in our numbers, we have negative 7.5 minus positive 10 divided by negative 3.5. This gives us time equals 5 seconds. 4.2. The 5 uniform acceleration equations. The motion of an object moving with constant velocity is described by 3 variables and only 1 equation. The key variables for constant motion, constant velocity, are v, which is the symbol for velocity, unit is meters per second, d, which is the symbol for displacement, with the unit meters, and t, which is a symbol for time with the unit seconds. The equation for constant velocity is v equals d over t. This is the only equation that you can use if an object is moving with constant velocity. The motion of an object with constant acceleration is described by 5 variables. And unlike constant velocity, constant acceleration has 5 equations that will work for it. You can use any one of 5 equations if an object is moving with constant speed. The 5 variables that we use are Vf, which is final velocity in meters per second, Vi, which is initial velocity in meters per second, d, which is displacement in meters per second, or in meters, and a, which is acceleration in meters per second squared. T, time, is in seconds. The 5 uniform acceleration equations are equation 1. A equals Vf minus Vi over t. For this formula, we say d is dc. dc stands for we don't care. Because d is not in the formula, we don't care about it. This is going to be important a little bit later. The second formula is Vf squared equals Vi squared plus 2AD, where time equals don't care. The third equation is d equals VIT plus 1/2 AT squared. And in this case, Vf is the one we don't care about. The fourth equation is d equals Vft minus 1/2 AT squared, where Vi is the one we don't care about. And finally, the fifth equation is d equals Vf plus Vi over 2 times t. And this formula doesn't have acceleration in it, so we don't care. It's still a uniform acceleration equation though, because it has two speeds, Vf and Vi. You can tell which formula is the right one to use for a problem. By deciding which variable the problem doesn't use. This is the variable that we labeled dc when we wrote out the equations, or don't care. Here's an example that shows you how this works. A car is moving north at 30 meters per second when the light turns red. If it has an acceleration of 8 meters per second south, how far does the car travel? A big step in figuring out which formula we need to use is writing out our list. Vi is 30 meters per second to the north. This is positive 30 meters per second, because north is a positive direction. Vf equals 0. This is because the car is stopping at a red light. Stopping means 0 meters per second. The acceleration is 8.00 meters per second to the south, which is negative 8.00 meters per second. Displacement is our unknown, and t is the variable we don't care about. It's not mentioned in the problem at all. Because t is dc, we use formula number 2, which doesn't include time in it at all. Formula number 2 is Vf squared equals Vi squared plus 2AD. We can rearrange this for d. d equals Vf squared minus Vi squared over 2a. We can substitute in our values of 0 squared minus positive 30.0 squared divided by 2 times negative 8.00. This gives us a displacement equal to 56.3 meters. Since this is positive, we rewrite this as 56.3 meters to the north. Here's another example. Ben is waiting at a stoplight. When it turns green, he accelerates at 6 meters per second squared forward for 4.10 seconds. How far does he travel in this time? We start by making our list. Vi equals 0 meters per second. This is because he is not moving when he is stopped for the red light. The acceleration is 6 meters per second squared forward. Time is 4.10 seconds, and we're looking for displacement. Since it's not listed in the problem, Vf is don't care, and this tells us that we should use formula number 3. Because formula number 3 doesn't include the variable VF. This formula is D equals VIT plus 1/2 AT squared. And it doesn't need to be rearranged since displacement is already the variable in front of the equal sign. We can substitute in our values of displacement equals 0 times 4.1 plus 1/2 6 times 4.1 squared. This gives us a displacement equal to 50.3 meters forward. 4.3. Using gravity in the uniform acceleration equations. When an object is falling under the influence of gravity, it actually speeds up a little bit each second. In fact, it speeds up about 10 meters per second each second. This is because gravity is a type of acceleration. Gravity causes acceleration. On the surface of the Earth, the acceleration due to gravity is the same everywhere on Earth, or that's what scientists accept. If you were on the surface of another planet, you would find a different acceleration due to gravity depending on that planet's mass. The acceleration due to gravity on Earth is given by the symbol small g, not to be confused with big G, which we're going to use later on. And it equals 9.81. This is the value we'll use in Physics 20. G equals 9.81, and since it's acceleration, meters per second squared, the direction is down. This is really important. Since G is always down, G is always used as a negative in calculations. G is a form of negative acceleration. And here's an example that will show this. A rock is dropped from a 5.1 meter high bridge. How long does it take to fall? Well, to start with, our acceleration is g, which is 9.81 negative because it's down meters per second squared. Vi is 0 meters per second squared, or meters per second. The displacement is 5.1 meters, and it falls down. We have to be really careful to notice that this direction is actually down. It goes from a higher location to a lower one. When an object falls down, its displacement from start to finish is down. This means that it has a negative displacement. So displacement in this case is negative 5.1 meters. We're looking for time. Time is question mark. The formula that includes displacement, initial velocity, time, and acceleration is displacement equals VIT plus 1/2 AT squared. Now, normally we can't solve this one for t. Normally, this formula is much too hard to rearrange for t. This is because t is squared and not squared both at the same time in the equation. But in the case when Vi equals 0, it becomes much easier. This is because Vi is 0, therefore Vi times t also equals 0. And we can cross the VIT term completely out of the equation. And the equation just turns into d equals 1/2 AT squared. This can be rearranged for t. Rearranging this for t, we get t equals the square root of 2d over a. So now let's plug our numbers in and get an answer for t. T equals the square root of 2d over a equals the square root of 2 times negative 5.1 meters divided by negative 9.81 meters per second squared. And it's a good thing we put the negative in the 5.1 because now we have no negative under our square root and we get a time of 1.0 seconds. Our second example is a little bit trickier because we are going to have an initial velocity, but still have to use the same formula. A rock is tossed up at 10 meters per second from a window 25 meters from the ground. How long does it take to reach the ground? Sometimes when dealing with problems, it's best to start by drawing a picture to help visualize all the variables in the situation. So here's the window, 25 meters from the ground. This means overall, the distance that's going to fall from start to finish, it is a displacement of 25 meters. Even though the ball goes up and back down, the up and down part of the journey doesn't matter to the displacement. The initial velocity of 10 meters per second up is our initial velocity, and we're looking for time. Vi is 10 meters per second up. We write this as positive 10 meters per second. The acceleration is gravity, is 9.81 meters per second squared down, which is negative 9.81 meters per second squared. The displacement, and here's the important bit, is 25 meters down. It goes 25 meters from start to finish. Because it's down, this is negative 25 meters. The negative is so important to this calculation. Time is question mark. And normally we'd write VF is don't care. But in this case, do we? Maybe finding VF might be useful. Let's look at our formula. The formula we would normally use, this formula that doesn't include VF, or VF is our don't care variable, is D equals VIT plus 1/2 AT squared. But this formula is really hard to rearrange for t. If Vi is not equal to 0, remember in the last example Vi was 0 and that's why we were able to use it. So instead, we have to go about it another route. There's a sneakier way we can get at this time. It becomes a two-step problem. In the first step, instead of finding t, we're going to look for VF. And in the second step, we're going to use VF to find t. In an easier equation. So let's start with step 1, finding VF. VF squared equals Vi squared plus 2AD. So VF equals plus or minus square root vi squared plus 2ad. We have to be careful with this plus or minus. Normally we ignore it, but VF is a vector, so the negative actually does matter. At the end, the rock is falling down. Just before it hits the ground, VF, it's falling down. So that means we want to use the negative because of the down. This is going to be important in our calculations, and it will change the numbers. VF equals negative square root vi squared plus 2ad. VF equals negative square root positive 10 squared plus 2 times negative 9.81 times negative 25. The negative part of the 9.81 cancels out the negative part of the 25, and it actually changes what our calculations result would be. Negative 24.300200576 meters per second is VF. Don't round these intermediate answers. If you round too early, you're going to introduce error into your calculation. Save rounding for the very last. Now that we have VF, we can move on to step 2. Step 2 is finding t. Now we have VI as 10 meters per second. Acceleration is negative 9.81 meters per second squared. VF is equal to negative 24.300200576 meters per second. T equals question mark. Much easier formula that involves all these variables is A equals VF minus VI over T. Rearranging this one for T is much easier. T equals VF minus VI over A. So T equals negative 24.300200576 minus positive 10 divided by acceleration, which is negative 9.81. This gives us a time equal to 3.496453 ... seconds. And now we can round because we're on our last step and we need 2 significant digits. So this gives us time equal to 3.5 seconds.